out of the ice and then divvy it up in very small slivers of ice. That ice still contains air bubbles. So ice that you extract from 2 kilometers down in the Antarctic still contains air that's 800,000 years old. And so you can measure the amount of CO2, the amount of carbon dioxide in that air from 800,000 years ago. And that's the red line that you see. If you measure the amount of CO2 in those air bubbles of all of those little pieces of ice over 2 kilometers deep, you get the red line. It's the amount of CO2 in the atmosphere over the past 800,000 years. The black line you see is a temperature over that same period of time. Temperature gets technical, but if you take the amount of deuterium in the water of the ice, then you get a proxy for what the temperature is like. I'm not going to say much more about that. Why I'm showing these graphs is that there's some big conclusions you can draw out of these graphs. One, neither the amount of CO2 in the atmosphere nor temperature have been a constant over time. They've both been changing over time, right? Two, they've been changing in sync. When your red line goes up, your black line goes up. When your red line goes down, your black line goes down. That is the greenhouse gas effect. We know that since 1850. It was a woman scientist, by the way, who discovered it, that if you increase the amount of CO2 in the atmosphere, you will raise the temperature of your atmosphere. It's a physical law. Third big conclusion is if you look at the numbers on the vertical axis of CO2, you can see that over the past 800,000 years, the amount of carbon dioxide in the atmosphere has roughly varied between 200 and 300 parts per million. Never much less than 200 and never more than 300. There's a question to the audience. Does anybody have any idea at what amount of parts per million CO2 we measured in the atmosphere today? Any guesses?